Hello everyone and welcome to this introductory video on deep learning, a crucial field in the world of AI and machine learning. In this series, we will explore the fundamentals of deep learning, its key concepts and architectures, and how it's transforming the industries like healthcare, robotics and autonomous systems. So whether you are new to this subject or looking deep in your understanding, this series will provide the insights, examples and you can say hands-on practices. We will begin with a brief overview to set the foundation, then dive into the core topics chapter by chapter. So let's embark on this exciting journey into deep learning. So, introduction to deep learning. Deep learning is a subset of machine learning we know about. So, it is inspired by the human brain's neural network. It deals with the algorithms that attempt to model the high level abstraction in the data through the layers of processing. Paradigm of learning in deep learning focuses on supervised, unsupervised, and reinforcement learning. With the advent of powerful computing, deep neural networks can now solve the complex problems like image recognition and natural language processing. However, it also presents the challenges such as overfitting, high computational cost, and data scarcity. So, deep learning is a constantly evolving field with new techniques and breakthroughs. Researchers continue to work on improving the architectures, regularization methods, and model efficiency. A solid foundation in these concepts will allow you to dive into the more complex topics in this field. This chapter introduces you to major components and the practical applications of deep learning. The ability to use deep learning effectively requires both theory and hands-on experience. So now, feed-forward neural network. Feed-forward neural network or FNN are the simplest type of neural network architecture. This network consists of an input layer, one or more hidden layers, and an output layers. Each node in a layer is connected to every node in the next layer. Hence, the term feed-forward. Activation functions like ReLU or sigmoid, these are the mathematical functions, are used to introduce the non-linearity, means the data sets or data features relationships is linear or not. If non-linear, so this allows the models to learn the complex patterns. The depth of the network, determined by the number of hidden layers, influence its learning capacity. In multilayer neural networks, backpropagation adjusts the weights to minimize the error between the predicted and actual outputs. These networks are foundational for understanding more complex architectures like convolutional neural network. Cardinality refers to the number of units in each layer and plays a role in determining the complexity of the model. Properties of fuzzy relations can be applied to FNN to handle the uncertainty in the data. So, training the neural network. Training a neural network involves optimizing the models to minimize the loss function using a process called backpropagation. Backpropagation computes the gradient of loss function with respect to the weights and updates the weights to reduce the loss. The risk minimization approach helps to generalize the model, preventing the overfitting. So loss functions like mean squared error or cross entropy are commonly used for regression and classification tasks respectively. Regularization techniques like the L2, L1 regularization helps to prevent overfitting. Optimization algorithms such as gradient descent and Adams are widely used to find the optimal weight. Model selection involves choosing the right architecture and parameter that best fit the data. Hyperparameter tuning plays also a crucial role in improving the model's performance. So training the deep models can be computationally expensive, but techniques like batch processing and GPU acceleration helps to manage the workload. So the balance between the training time, model accuracy and overfitting is a key aspect of training the neural network. So now, conditional random field and hidden Markov model. Conditional random fields are a class of statistical models used for a structured prediction, where the output is a sequence or set of related outputs. They are used for tasks such as sequence labeling, where the goal is to predict a label for each element in the input sequence. CRFs model the conditional probability of the output given the input. The linear chain CRF also there. So in these models, the partition function ensures the proper normalization of the probability distribution. See, these terminologies can be hard, but we will discuss in each topic in the detailed format. So belief propagation is also a method for computing the marginal probabilities in the CRFs. So hidden Markov model are similar to the CRFs but are limited to their assumptions of independence between the states. Hidden Markov models are also used in natural language processing and also in the speech recognition and bioinformatics. Okay, so both CRFs and hidden Markov models have been foundational in sequence modeling and have influenced modern approaches like the recurrent neural network. So understanding the CRFs and hidden Markov models gives the insights into the evolution of sequence modeling in the deep learning. So advanced deep learning architecture. Advanced deep learning architecture like deep feed-forward network, CNN, RNN are key to solving the complex real-world problems. Deep feed-forward networks have multiple layers that can learn increasingly abstract relations of data. Regularization techniques like dropout, batch normalization, and weight decay are used to prevent the overfitting in deep models. Training the deep network requires efficient backpropagation, which can be computationally intensive, and innovations like GPU acceleration have made this feasible. Convolutional neural networks are designed for spatial data such as images and use the convolutional layers to extract the hierarchical features. CNNs have revolutionized the image recognition and are also used in speech and video analysis. Recurrent neural networks are designed for sequence data where the output at each step depends on the previous one. Recurrent neural networks are widely used in natural language processing and time series forecasting. Another network like the deep belief network. These are the type of generative model that learns to represent the data in terms of probability distribution. So now deep learning in research and applications. Deep learning has significantly impacted the fields such as object recognition, computer vision, and NLP. Object recognition tasks involve detecting and classifying the objects within the image, a challenge made possible by CNN. Sparse coding is a method for representing the data using the fewer non-zero coefficients is often used in unsupervised learning to extract the important features. In computer vision, deep learning techniques are employed for image classification, object detection, and semantic segmentation. In NLP, deep learning models like RNN and transformer are used for tasks such as sentiment analysis, machine translation, and text generation. So lots of applications are there. Deep learning models excel at feature extraction and pattern recognition in large, high-dimensional databases. The research in deep learning is moving toward more interpretable models and reducing the dependencies on vast amounts of labeled data. Transfer learning also there. Okay, so you can stay at the forefront of deep learning advancement by understanding this application. So thank you for watching this overview video on deep learning. We hope it sparked your interest and gave you a solid introduction to what lies ahead. In the upcoming chapters, we will explore the key techniques and models in more detail, providing you with the knowledge to apply deep learning in real world scenarios. So don't forget to subscribe, stay tuned for the next video and keep learning. See you soon.